This is a presentation of Chapter 10, Section 6 in the 8th grade book entitled The Fundamental Counting Principle. Now, we already talked a little bit about the counting principle when we were multiplying probabilities together earlier in Chapter 10. So you already have a little bit of exposure to this, but here's now time to put this and give it some formal meaning and definition in our lives. So what is the fundamental counting principle? It says formally, if one event has m possible outcomes and a second has n possible outcomes after the first event has occurred, then there are m times n total possible outcomes for the two events. And that can be extended, that definition can be extended when you have more than two events. You just keep multiplying by whatever the next probability is on down the line until you reach the final one necessary. Again, it says if one event has m possible outcomes and a second has n possible outcomes after the first has occurred, then there are m times n total possible outcomes for the two events. Tree diagram. Tree diagram is a branching diagram that shows all the possible combinations or outcomes of an event. That's a branching diagram that shows all the possible combinations or outcomes of an event. Alright, so let's go ahead and start taking a look at our examples here. Number 1 says license plates are being produced that have a single letter followed by 3 digits. And we're supposed to find the number of possible license plates. So we start off there and we see that the first spot has to be a letter. Well, there's 26 different letters in our alphabet, so that means there's 26 different letter choices for the first spot on the plate. So that's why the first thing they've written here is 26. Then the next spot can be a digit. So when we're talking about single digits, there's 10 options there, 0 to 9. So that's why they wrote 10. The next spot is another digit, so that's why they wrote another 10. And then the final spot is another digit, so we wrote another 10. Now, why does that matter? Well, we're going to use the fundamental counting principle to find the total number of possibilities here. I'm going to take and multiply all these together to find out how many different license plates I can make from that layout. So I'm going to multiply together my 26, my 10, my 10, and my 10, which I don't really need a calculator for. And when I multiply that together, I get 26,000. So with 4 spots, with a letter, and then a digit, and a digit, and a digit, in that order, I have 26,000 possible license plates I can make. Now they're asking me to use that to find the probability that the license plate has the letter Q. Well, obviously that involves our 26,000 because we know probability is going to be a comparison to the number of possibilities. The number of possibilities is 26,000. We just have to figure out how many ways it works then with Q and write that as a fraction, as our final answer, as our probability. So there's only one way I can have Q in the first spot, and that's if I write Q in the first spot. So there's only one way that can happen, which is you can see what they've written right here. But then the next 3 spots can still be anything. They can be any number. They didn't say anything about the numbers. The only thing said is they want Q there. So that's why they wrote 10 in the second, and the third, and the 4th spot. Exactly like we did here. Because I can have any of 10 numbers here, and any of 10 numbers here, and any of 10 numbers here. So we multiply all those together, and we end up with, in this case, 1,000. 1,000 over 26,000. Now, as you can see, they've reduced that, kind of chopping off some zeros here, and we end up with 1 over 26. So there's a 1 out of 26 chance that you're going to have a plate with the letter Q in it. They divide that out and they get a decimal, and we end up with 0.038, where you've got about a 3.8% chance of getting a license plate with the letter Q in it. All right, now they're asking us to find the probability that a license plate does not contain a 3. So we're still using that same number we computed earlier, that 26,000, but now we've got to come up with a plate that doesn't have a 3. So the first spot, again, remember, that was a letter. Well, any of 26 letters will work there. That's not a problem. Now, these next 3 spots are the numbers. Well, we have to actually go ahead and figure that out here then. Well, if I take out the 3, there's still 9 single-digit options that will work in each spot. 0, 1, 2, 4, 5, 6, 7, 8, and 9. So there's 9 options there for the first spot, 9 options for the second, and 9 options for the last. So to find the number of possibilities there, I'm going to multiply all these together. And I get 18,954. So the probability of not getting a 3, probability of no 3, is 18,954 over 26,000. As you can see, they've reduced that fraction down to 729 over 1,000, which in terms of a decimal is 0.729, or in terms of a percent, 72.9%. So there's a 72.9% chance that I can pull a plate without a 3. All right, let's go ahead and take a look at number 2. It says you have a photo that you want to mat and frame. You can choose from a blue, purple, red, or green mat and a metal or wood frame. Describe all the ways you could frame this photo with 1 mat and 1 frame. So now what they're talking about here is that concept of a tree diagram. Tree diagram is a branching diagram that lists all the possibilities here. So it's a tree at multiple levels. In each level there is going to represent the choices you have at that level. So the first thing they said to us is you have a choice of a mat color. And at that level you could choose blue, purple, red, or green. So as you can see, they listed here in a column blue, purple, red, and green. And they made a little illustration to show you there that the shaded area would, of course, be the mat. So they're helping us to remember that that level of choice is the mat. And then I go down to my next choice. And then I'm choosing what type of frame I want. I can have metal or I can have wood. So as you can see, underneath each one of those is listed metal and wood. Because, for instance, I could pick a blue mat and a metal frame, or a blue mat and a wood frame. I could pick a purple mat and a metal frame, or a purple mat and a wood frame. And we go on down the list there until we've created all of our possibilities. Well, from the counting principle, we knew that there was 4 options here for the mat color, and 2 options here for the frame type, metal or wood. So we know there's 8 different ways to frame the photo. What's nice about the tree diagram is it actually lists them. We can have a blue mat and a metal frame, a blue mat and a wood frame, a purple mat and a metal frame, a purple mat and a wood frame, a red mat and a metal frame, a red mat and a wood frame, a green mat and a metal frame, or a green mat and a wood frame. That's what a tree diagram does that's different than the counting principle. The counting principle just gives me a number. And we saw that in action right here. But it doesn't list. The branching diagram shows me the list. And perhaps it's easier than just trying to list them out and remembering what you've actually written or have not written it, and so on and so forth. Obviously, where a branching diagram becomes troublesome is if there's a really long list of possibilities. If we were to go back to that question we just did with the license plates, and I said list out all the possibilities of the license plates, and you had to list the 26 letters at the first level, and then the 10 numbers at the next level, and then 10 numbers on a third level beneath that, and 10 numbers on the fourth level beneath that, you're going to quickly see, or recall from that number we ended up with, that you're going to have a massive tree diagram that lists tons and tons and tons of options. All right? Is it a way to write a list if we need to? Yes, absolutely. Do we want to list it if it's something that works out to be 26,000 options? No, probably not. But when we have a small list like we have here and they ask us to list the options, the tree diagram or the branching diagram might be the best possible option. All right, let's go ahead and take a look at number 3. There are 7 black socks and 2 white socks in a drawer. 2 socks are removed. What is the probability that the colors match? All right, so as you can see, they made a little table here, and the table lists the different possibilities for the first and the second pull. So let's say I pull a dark sock first. Well, to pull a dark sock first, all right, I have a 7 out of 9 chance of pulling a dark sock. Why? 9 total socks, and 7 of them would be the dark socks. Now, when I go for pull 2, there's 8 socks left, so notice the bottom number in my probability has become 8. The top then represents whatever scenario happens. There would be 6 dark socks left if I pulled a dark sock first, so that's 6 out of 8. If I pulled a dark sock first, there would still be 2 light-colored socks left, or 2 white socks. So 2 out of 8 there. So to find the probability of pulling a dark and a dark, I'm going to multiply those probabilities together. My 7 9ths and 6 8ths, which you can see they reduced to 3/4, which is 21 over 36, or 7 out of 12. To find the probability of the dark and the white, which we don't really need, but because they're asking about the colors matching, but to find that probability, we would do 7 out of 9 times 2 eighths, which they reduced to 1/4, and they got 7 out of 36. Now, let's say instead they started with the white sock. Well, you've got a 2 out of 9 chance of picking the white sock because there's 2 whites in the drawer out of 9 total possible socks, which is what you can see that's written right here. Pull 2, I go for the black sock. Well, there's 8 socks left in the drawer, but there's still 7 darks left because, remember, I pulled the white sock to begin with. So that's 7 out of 8. If we're going for the white sock again, there's still 8 total socks left in the drawer. Remember, I already removed one in the first pull, but there's only 1 white sock left here. So that's 1 out of 8. Again, to find my combined probabilities, I'm multiplying. So I'm going to take my option here for white and dark would be 2 out of 9 times 7 eighths, which is what you can see right here, 14 out of 72, or 736. For white and a white, it would be 2 9ths times 1 8th, which is what you can see right here, which is 2 72nds, or 1/36. Now, we did a lot of work, but we really haven't answered the question, because the question asked me what's the probability of picking socks that match. So I can be looking to pull a dark and a dark, or white and a white, because those would be socks that match. So we know that the option for dark and dark is 7 out of 12 from up here. We know the possibility for white and a white is 1/36 from down here. Well, to find the combined probabilities, I'm going to add those two things together. And when I add those two things together, I get 11/18. Remember, I already did the multiplying. You might be saying, well, why didn't we multiply down here? We already found the combined probabilities of these matches up here. It's just a matter of me adding up the percentages now, or the probabilities, to find my combined answer. So when I add these two guys up, common denominator would be involved there, I end up with 11/18, or in other words, there's a 0.61 or a 61% chance of me pulling matching socks based on the scenario described. All right, let's go ahead and finish by looking at the check it out examples here. Number 1 says Social Security numbers contain 9 digits. All Social Security numbers are equally likely. Find the number of possible Social Security numbers. So there's 10 digits available for each spot. Numbers only. So 0 to 9, 10 possibilities. So we've got 9 spots to fill in the card. 4, 5, 6, 7, 8, 9. There's 10 possibilities for each spot. So I'm going to take the number of possibilities I have at each spot and multiply those together to find the total number of possibilities. And when I multiply that together, I get 1 billion. So there's 1 billion possible Social Security numbers that consist of 9 digits. Number 2, a baker can make yellow or white cakes with a choice of chocolate, strawberry, or vanilla icing. Describe all the possible combinations of cakes. Now, as you can see, they've listed the possibilities, but how they came up with that list would certainly be with the tree diagram, which is what they're asking us to work for here. So let's go ahead and make a little tree diagram that matches that list. We know we can make a yellow or white cake. So that's my first choice. So I'm going to list a level that lists yellow and white. Now, after I get yellow or white, I can then get three types of frosting: chocolate, strawberry, or vanilla. So underneath each one of those now, I have to list my next combination, my next list of possible combinations there. So chocolate, strawberry, or vanilla under each. Now I'm going to abbreviate here: chocolate, strawberry, vanilla, chocolate, strawberry, vanilla. So we've got yellow and chocolate, yellow and strawberry, yellow and vanilla, which is exactly the first three we saw. White and chocolate, white and strawberry, white and vanilla. Does this work out? Well, let's see. We ended up with, as you count them up, 6 different possibilities there. Well, 2 possibilities here and 3 possibilities here. Using the counting principle, multiplies out to make 6. So our number should be 6. Since we ended up with 6 possibilities, that makes good sense.